Hello guys, my name is Nathaniel Miller, and I'm going to talk to you about Richard von Mises' The Birthday Problem. First, a little bit of probability theory history. In 1550, Cardano addresses the probability of certain outcomes in the rolls of dice. He also presents a crude definition of probability. In 1654, Pascal and Fermat lay fundamental groundwork of probability theory while working on a gambling problem posed by Mir. The question was, what were the number of turns required to ensure obtaining a 6 in the roll of 2 dice? In the 17th century, Grant sets out to predict mortality rates by categorizing births and deaths. In 1657, Huygens publishes the very first text on probability theory, which title translates to On Reasoning in Games and Chance. In 1713, 8 years after his death, Bernoulli's works were published, containing still relevant probability results as well as the famous Bernoulli theorem. In 1812, Laplace outlines the evolution of probability theory in Théorie analytique des probabilités, and he also provides the current definition of probability as well as fundamental theorems of addition and multiplication of probabilities. So the birthday problem. What the birthday problem is how many people must be in a room before the probability of 2 people in the room sharing the same birthday. Now, when working on this problem, the first thing you have to understand in probability is that the probability of an event happening plus the probability of an event not happening equals 1. So we're trying to figure out an event happening, which is 2 people sharing the same birthday, which you can write this, since the first statement's true, you can write this a different way. The probability of the event happening equals 1 minus the probability of the event not happening. And in this case, we're talking about 2 people sharing the same birthday. Now, if you were to go about this, trying to find out the probability of 2 people sharing the same birthday, really you could just go down the line. It would be the first person has a pick from any of the 365 days. They're going to be 1. And then you multiply that by the 1 birthday for the next person divided by the days in the year, because that's the chance. So what you're going to find out is that it equals 0.27%. And you could do this, that's for 2 people, the chance that the 2 people have the same birthday. You can do it for 3 people, it would just be 2 over 365. You could just keep adding people and just keep going this way till you find out you're going to end up with 1/83 183. I think it's 183 before you hit over 50%. However, the way this is actually solved is by looking at the probability that the event doesn't happen. And when you're looking at the probability of the event not happening, you end up doing the opposite thing. You'll be doing like 364 over 365 times 363 over, sorry. $63 over 365 times, that, how many people you go. Right there, that would be 3 people. The chance that 3 people don't share the same birthday. Don't share the same birthday. If we add another one, you'd have 4. You'd be 362 over 365. I know, I'm sorry if this is hard to read, and your percent chance that they don't share the same birthday would be about 98.36. That's percent. So if we take that, it would be, in decimals, it would be 0.9836, right? If you subtract that from 1, you're gonna end up with 0.0164. So about 1% chance that 2 people would share the same birthday. Now there's a simpler problem that you can use to do this, and it's using factorial. So it's n, where n equals the number of people, times 365 choose n over 365 to the nth. And that's all equal to P, the event doesn't happen. So that's your formula for figuring out the event doesn't happen. Use yellow, make it smaller. So, if you're trying to find out the probability of the event happening, we know that the probability of the event happening equals the probability, 1 1 minus the probability. One minus the probability of the event not happening. Since we know the probability of the event not happening is n factorial times 365 choose n over 365 to the n, you could rewrite the probability of the event happening equals let me get ahead of myself here. Equals 1 1 minus n factorial times 365 choose n over 365 to the n. Now the answer to this might be a little surprising. GeoGebra actually has a running simulation on this online you can play with depending on group size. But like it says here, when the paradox is n equals 23, the probability of having a birthday match is approximately 50%. So surprisingly, the answer is there's only need 23 people in a room to have a 50% chance that two of them will share the same birthday. And this leads to the next part, which is why is it called a paradox? Just the question itself, the statement itself, I should say, is just mind-boggling. It's a paradox because it's hard to fathom that only 23 people are needed for there to be a 50% chance of a shared birthday, because there's 365 possible birthdays in a normal year. And people just can't see that 23 is such a low number compared to the amount of possible birthdays. The other thing is, the question's often not interpreted correctly. You're asking, they're just saying a 50% chance, not a 100% chance. A lot of people think what this is saying is that when there's 23 people in the room, there's going to be two people with matching birthdays. That's not what the statement is. And then the last thing that really makes it a mind-boggling thing is it's not a self-oriented question. It just says two people in the room share a birthday. Not that you share a birthday with one of the people in the room. And a lot of people tend to self-orient the question when they're looking at it. So that's a few reasons why it's perceived as a paradox. Then the last thing I want to touch on is how probability is applied in today's world. It's actually used a lot, and not in like just math studies, but for weather forecasts, when they say 60% chance of snow, that's a probability. Elections, they predict who's going to win. Disease statistics, 3 times higher risk of strokes. Car industries for recall and production, military risk assessments, and gambling, sports gambling. All these are common uses today. And the last thing I want to leave you with is the list of resources I used for this. Thank you.